Hey mathletes, this is a video on improper integrals, type 2. So make sure you've already watched my video on type 1 improper integrals because those are a bit different. They have infinite limits. Now with type 2 improper integrals, rather than having infinity or negative infinity as one of your limits of integration, you're just going to have functions that are undefined for at certain points in the interval where you're integrating, rather. Okay, so we'll see exactly what I mean. But basically, type 2 means undefined for one or more values in a definite integral. Okay, that's the basic idea there. So you're going to get undefined, which is obviously when you divide by 0. Okay, so if you end up dividing by 0, or also if you have the square root of a negative number, that would also give you something that's not a real number. Okay, so that the function would not be defined there, so it would be undefined. For the square root of a negative number or for dividing by 0. Okay, and usually it's going to be one of the two limits of integration, but you could also have the values for which it's undefined be halfway or somewhere in the middle, as opposed to the lower limit or the upper limit. Alright, so let's see an example so you can see exactly what I'm talking about here. Okay, so example. The instructions say the integral converges. Okay, the integral converges. And when they say the integral converges, they just mean that our answer isn't going to be infinity or negative infinity, and it's also not going to be undefined. Okay, and they want us to evaluate the integral. Evaluate the integral. And on my math lab, they say evaluate the integral without using a table. I'm okay with you using a table if that's how you like to do it, but I'm not going to teach you how to use a table because that's just not how I do them. Okay, but if you use a table and that's what you're good at, you're welcome to use a table. Okay, so example number 1 is the integral from 0 to 324 of dx over the square root of 324 minus x. Okay, so the integral from 0 to 324 of dx over the square root of 324 minus x. So here, the value for which this original function is undefined is going to be the 324. So if we plug in 324 into this denominator, we're actually going to get 0. Okay, so we've got our two limits of integration, x equals 0 and x equals 324. And notice that if we plug in 324 for x, this is undefined. Undefined at x equals 324. Okay, so technically what you're supposed to do in this situation is you're supposed to remember that, and then when you're doing, after you've done your antiderivative, you're supposed to write it as a limit. Okay? So, because the original function is undefined at x equals 324, because we'd be dividing by 0, we rewrite it as a limit. Okay, so write as a limit. And because it's the upper limit of integration, the basic idea here is we're integrating from 0 to 324. And the upper limit of integration is 324, so that's the one we're going to be writing as a limit. Okay, so the way we rewrite it is we write it as the limit as c goes to 324, and then it's going to be from the integral from x equals 0 to x equals c. Okay, so it's a little bit strange the way they write it. And the reason they write it as a limit is because technically, if your original function is undefined, you do have to write it as a limit. So let me write that a little bit more clearly. Okay. So it's the limit as c approaches 324 of the integral from x equals 0 to x equals c of dx over the square root of 324 minus x. Okay, and it's actually going to be the limit as x approaches 324 from the left side. And the reason for that should be clear if you look at the graph. Now remember, if you don't have a graphing calculator, you can always go online to GeoGebra. So you just open your browser, okay, and then you go to GeoGebra graphing calculator. You can just type that in your search engine. And then graphing calculator GeoGebra. And then you can just type in your function. So in this problem, our function was 1 over the square root of 324 minus x. Okay, so 1 over the square root of 324 minus x. Okay, if I press enter there, then we've got our function here. And then if I go ahead and zoom out, we can see better what's going on with this function. So it's a very steep function. It starts out almost flat, and then remember, we're integrating from 0 to 324. And as you can see here at 324, we have the function is undefined. So that's why we actually want to take the limit as x approaches 324 from the left, because we're going from here, which is 0, to 324, which is right there. Okay, that's 324. And the limit as c approaches 324 from the left is actually going to give us the value that we need. Okay? So that's what we're going to be doing there. And it's from the left because it's from the left on the picture. Okay, but none of this really matters that much, because when you're doing these problems, even though you're supposed to do all this technical stuff, you really just end up plugging in the number at the end anyway. So it's not quite as bad as it looks. I'm mostly teaching you how to do it the correct way, but honestly, these are not that hard. They're a lot easier than the type 1 improper integrals. So we're only going to do a couple examples. Okay, so for this one, to integrate this function, what we're going to have to do is, instead of writing it as 1 over square root of 324 minus x, we're going to go ahead and move that to the numerator. Okay, so that's going to be 324 minus x, quantity to the negative 1/2 dx. Okay, and we still have our integral and our limit. Okay, and then we're going to have to do a u substitution here. So as usual, when you have a composite function, you want to let u be the inside of your composite function. So here we're going to let u equal the inside of our composite function. So that's going to be 324 minus x. So that means du equals negative dx, which means that dx actually equals negative du. If you solve for dx, at least that's the way I usually teach people because it's less confusing than the way that our book does it. So anyway, what we got here is we got the integral, the limit of the integral of u to the negative 1/2 times negative du. Okay, so we have the limit of the integral of u to the negative 1/2, right? Because we said 324 minus x was our u. And then dx, we just said, was negative du. So we're going to have a negative du here. All right? And then if we integrate that, we can just use the power rule. So we add 1 to the exponent, and then we divide by the new exponent. So that's going to give us u to the negative 1/2 plus 1 divided by negative 1/2 plus 1. And then as for the minus, we can factor that out front. We can actually even factor it out of the limit. Okay, so we have negative limit as, well, we're not going to write the limit in yet. And then here's our antiderivative. So we got u to the negative 1/2 plus 1 divided by negative 1/2 plus 1. Okay, and then negative 1/2 plus 1 is positive 1/2. Okay, so here we have u to the positive 1/2 divided by 1/2. And we're taking negative limit of this. So if you're dividing by 1/2, that's same as multiplying by the reciprocal, which is 2 over 1. So if I flip this over, I can factor out the 2. Okay, so if I bring the 2 outside of the limit, then we're going to have negative 2 times the limit of u to the 1/2. And now that we've got it in the form u to the 1/2, we're going to go ahead and plug back in the original expression for u in terms of x. Okay, so we're going to plug in 324 minus x for u. Okay, so we have negative 2 times the limit of 324 minus x, quantity to the 1/2. So remember, the 1/2 power is the same as the square root. Okay, so really what we have here is negative 2 times the limit as c approaches 324 from the left of the square root of 324 minus x. Okay, and then don't forget this whole thing, even though we have a limit built in, it's actually a definite integral. So now that I'm at the end, I'm going to go ahead and plug in these values we had for the definite integral. And we're going to want to plug in the values after we got the limit written out, because this original value of 324, the original function was undefined, so that what was inside of the integrand was undefined. So that's why we had to write it as a limit. Okay? So we're going to be plugging in, we're going from 0 to c. X equals 0 to x equals c. So I'll go ahead and write that in here. So we're going from 0 to c. And then plugging in the top number into the function, and then we subtract the function and evaluate at the bottom number. Okay, so we still have negative 2 times the limit as c approaches 324 from the left. Plugging in, we have the square root of 324 minus c minus the square root of 324 minus 0. Okay, and like I said, even though I'm showing you the technically correct way to do it, really at the end you just end up plugging in this value for c. So these problems aren't actually that hard. It's mostly just notation, like what you're supposed to write down, but in the end you end up plugging in anyway. So some people actually skip writing the whole limit business because it doesn't usually end up affecting anything. Okay, but that's up to you. I'm showing you the correct way to do it, even though the correct way takes a little bit longer. It's good to know the correct way. So you're basically just going to be plugging in 324 in for C right there. Okay, so plug in. Okay, because that's how you do limits, right? When you're doing a limit, the first thing you do is plug it in and see if it works. As long as it's not undefined in your answer like this, you just plug it in. Okay, so we got the square root of 324 minus 324 minus the square root of 324. And then we've done the limit, so we still have a negative 2 out front. Okay, and then where do we go from here? Well, 324 minus 324 is 0, and the square root of 0 is 0. Okay, so this is 0. So we really have negative 2 times negative root 324. Okay, and I don't know what the square root of 324 is because my times tables doesn't go that far. So we're going to go ahead and use a calculator. I'm just going to use this calculator here for convenience. So 324 and then square root is 18. Okay, it's 18. And then of course these minuses are going to cancel out. Okay, so here we just have 2 times 18, which is 36. Okay, so our answer to this problem is 36. And keep in mind that all of these improper integrals are definite integrals. You probably have started to notice that. With improper integrals, you pretty much never would have an indefinite integral, at least not in our homework. Okay? Alright, so that's our first example. So I wanted to do another one. Or maybe 2 more total. Okay, so example number 2 is up next. So for example number 2, what we've got is the integral from negative 125 to 27 of dx over x to the 1/3. Okay, so that's going from x equals negative 125 to x equals 27. Alright, when you're doing these problems, I'm going to once again show you the correct way to do it, but the correct way is a little bit longer than just doing the problem the way it's written and then plugging in things at the end. So the correct way is a bit longer, but what you're supposed to do here is you're supposed to split this up into 2 integrals, and each integral needs to have a limit to avoid having a value that's undefined. So you might be wondering, well, Mr. Shoemaker, how would this be undefined? Well, remember, an integral actually goes from this number all the way up to that number, and it's continuous, which means it's taking the area under everything from negative 125 all the way up to 27, which means we're going to have to pass through 0. Okay, so somewhere along the way here, okay, 0 is somewhere in there, and if we plug in 0, we're going to be dividing by 0, which is undefined. Okay, so what we do is since 0 gives us undefined, so let me write this a little bit differently. Plugging in 0 gives undefined. So once again, we're going to have to write it as limits, but the way we're going to write the limits is we're going to need to write it as 2 integrals, which is a bit of a pain, honestly. but this is the way you're supposed to do it. Okay, so if you plug in 0, that gives undefined. So we're going to write it as two integrals with limits. Now it's not really that difficult, it's just a little bit obnoxious the way you have to do it, or the way you're supposed to do it. Okay, so how are we going to do this? Well, because 0 gives undefined, we write as two separate integrals with limits. So how's that going to work? Well, basically we're going to go everything from negative 125 to 0, and then we're going to do everything from 0 to 27. So those are going to be our two integrals. So we can rewrite this as the integral from negative 125 to 0 of dx over x to the 1/3 plus the integral from 0 to 27 of dx over x to the 1/3. And remember, that's one of the rules of definite integrals. It says that if you have a definite integral, you're allowed to split it up into smaller parts, as long as when you add up all the parts, you're covering the full range of numbers. So here we're going from negative 125 to 0, and then plus 0 to 27. But when you add them together, you're still going to get negative 125 to 27, so it is actually the same. And then, like I said, because 0 is undefined, you need to rewrite it as a limit. Okay? And it can be a pain to write it this way. That's why I say some people skip this altogether. But I'm trying to show you the correct way to do it. Okay? So what we got here is the first one's going to be the limit as c approaches 0 from the left of the integral from negative 125 to c of dx over x to the 1/3. Now the reason that one's from the left is if it's your upper limit of integration, it's always going to be from the left. Whereas if it's your lower limit of integration that's undefined, then that's always going to be from the right. And that should be clear to you by looking at the graph. Okay? So if you look at the graph of, here we have 1 over x to the 1/3. Okay, so if we do 1 over x to the 1/3 in GeoGebra, we're going to get a graph here. And we're going from, like we said, negative 125 to 27. So what's going on with the graph here is, here's negative 125. I zoomed in with my mouse. We're going from here all the way through 0. As we can see, if we zoom in here at 0, the graph is actually undefined. But we're taking the limit as c approaches 0 from the left. As you can see, that's going to give us this limit from the left. And then we're also going to do the limit as some other letter approaches 0, and that one's going to be from the right for our lower limit of integration of the second integral. Okay, and then we're going all the way over to, what was it, 27? Is that what we said? 27, yeah. So as you can see, the weird stuff is happening here because we have a vertical asymptote at x equals 0. So that's why we're having to do this weird stuff with limits. Okay, so the first one is the limit as c approaches 0 from the left. That's going to give us this one. And then the other one is going to be the limit as, I'm going to call it as d approaches 0 from the right. So that's going to give us this one here. And that'll be with this other integral. So this is going to be going from d to 27. Okay, so for the other one we have plus the limit as d approaches 0 from the right of the integral from d to 27 of dx over x to the 1/3. Okay, and then all we have to do from there is actually just find the antiderivative. But these ones are actually the same antiderivative or indefinite integral, so we can just calculate it once. So remember, 1 over x to the 1/3, if we move it to the numerator, it's going to become x to the negative 1/3. Okay, so we've got the limit of the integral of x to the negative 1/3 dx plus another limit of an integral of x to the negative 1/3 dx. Okay, and there we can just use the power rule. So we add 1 to the exponent and we divide by the new exponent. So what is negative 1/3 plus 1? Well, that's the same as 1 minus 1/3, which is 2/3. Okay, so using the power rule there, we actually just get x to the 2/3, and then we have to divide by our new exponent. So we get x to the 2/3 divided by 2/3, and then we still have our limit out front. And we have the same thing over here. Since this is the exact same expression, this other one is also going to be the limit of x to the 2/3 divided by 2/3. Okay, so that's the antiderivative that we did there. And remember, if you're dividing by a fraction, that's the same as multiplying by the reciprocal. So we go ahead and we flip over the 2/3 for each of these. And then we can factor it out front. Okay, we can actually factor it out of the limit. So we're going to have a 3/2, and we bring that out front. So now we have 3/2 times the limit as c approaches 0 from the left of x to the 2/3. And this is going to be evaluated. The first one we said goes from negative 125 to c, right? That's how we rewrote that first integral. It goes from negative 125 to c. Limit as c approaches 0 from the left. And then the other one was the limit as d approaches 0 from the right of the integral from d to 27. So that's this one here. So once again, we're going to have a 3/2 that we factored out front, and then we have the limit as d approaches 0 from the right of x to the 2/3 evaluated from d to 27. Right? Evaluated from d to 27. Okay, so we got all that written down. And then remember, we're just going to be plugging in these numbers into each of these. So for the first one, we plug in c, so we get c to the 2/3 minus, if we plug in negative 125, we get negative 125 to the 2/3. Right, so that's evaluating that limit. And then we still have a 3/2 out front. And then the same thing over here, plugging in the top number first. So we're plugging in the 27 first. So we have plus 3/2 times 27 to the 2/3 minus d to the 2/3. So that's plugging in the bottom number. Since remember, even though we have limits here, this is still a definite integral. Okay, and I forgot to write my limits, so let me write it. Let me actually factor out these 3/2. Okay, and I'm going to go ahead and write this as a limit. So limit as d approaches 0 from the right. I think I'm going to have to zoom out. This is getting pretty crowded. Okay, and then I factored out a 3/2 from the whole thing. And this one over here is limit as C approaches 0 from the left. Okay. But when all is said and done, even if you write it this way, which is kind of complicated looking, at the end you're still just plugging in the numbers, which is why some people skip the whole business with limits, because in most cases it's not really needed. I'm showing you the right way to do it, but I'm not saying it's the fastest way. The fastest way here would be to just plug in the numbers like you usually do and hope that everything works out, because it usually does. Okay, but plugging in here, we've got 0 to the 2/3 minus negative 125 to the 2/3 plus 27 to the 2/3 minus 0 to the 2/3, and then out front of the whole thing we have a 3/2. So of course 0 to any other number raised to any other power is 0. Okay, so this is 0, this one is 0. And then for the negative 125 to the 2/3, there's a couple ways you could do it, but remember the 2 is in the numerator, and if you square negative 125, the minus is going to go away. Okay, so I can cross out this minus there. And then if we do it on our calculator, we can just do 125 squared and then do the cube root of that. Or even easier, we can do 125 and then just raise it to the 2/3 power. Okay, so if we do 125 to the 2/3 equals 25. But of course there's still a minus out front, so it's going to be negative 25 because there was still this minus here. Okay, so we have negative 25 plus, well, what's 27 to the 2/3? Well, the cube root of 27 is 3 because 3 cubed is 27. And then 3 squared is 9. So this is going to give you 9. And of course, you're also welcome to use a calculator with that one as well. But I was able to do that one in my head. Okay, so we have a 3/2 times negative 25 plus 9. Okay. Alright, so we got 3/2 times negative 25 plus 9. And then we know that 25 minus 9 is 16. Okay, but because the larger number is negative, that's going to be negative 16. Okay, so what we got here is negative 16 times 3/2. Okay, and then if we cross out the 2 and the 16, we know that 16 divided by 2 is 8. Alright, so we're going to get negative 3 times 8, which is negative 24. Okay, so our answer here is actually negative 24. And because I'm a teacher who likes to always show people not just the correct way, but also the easiest way to do something, I have to point out here that even though I showed you the correct way with the limits, technically with this problem we could have just done it the old-fashioned way and not do any of the limits. So note, we just ended up plugging in anyway. Okay, so we ended up plugging in so limits weren't technically needed, I guess. Now, what I mean by technically is, technically we could get the right answer without the limits, but then on the other hand, we were supposed to do it with limits because that's the correct way to do it. Okay? But I'm just showing you the way you're supposed to do it, but if you want to skip the whole business with limits and just plug in, that works in most cases. So that could save you some time. But I would feel irresponsible if I didn't tell you about the limits business. Okay, so I just wanted to do one more. Okay, so example number 3. So for example number 3, we have the integral from 0 to 6. Okay, the integral from 0 to 6 of dx over the square root of 36 minus x squared. Now I'm going to continue doing it with limits because that's actually the correct way to do these problems. But like I said, you could, for most of these, if not all of them, you can get away with skipping the limits and just plugging in at the end. Because when you're doing a limit, you end up plugging in the number at the end anyway, which is kind of ironic. So the limits end up not usually being useful, but occasionally they could be, just not on our homework. Alright, so here, doing it the limits way, we can see that if we plug in 6 into this function, we're going to end up dividing by 0. Okay? So plugging in 6 is actually going to give us undefined. If we plug that in for x, 6 gives undefined. Okay? So the correct way to do it is with a limit. So we use a limit, and because it's the upper limit of integration, we're going to be doing the limit as c approaches 6 from the left. If it were the lower limit, it would be as c approaches 0 from the right, but here it's the upper limit that gives us undefined. Okay, so here we're going to have the limit as c approaches 6 from the left of the integral from 0 to, I'm going to go ahead and replace this 6 with c. So the integral from 0 to c of dx over the square root of 36 minus x squared. Okay? And that's how you set it up, the formally correct way. It's correct. Okay, and then how do we do this antiderivative here? Well, for this one, you might want to use your formula sheet. Okay, so let me pull up our formula sheet. Set college, Canvas, login. Okay. So, so for our formula sheet, I believe this one is going to be sine inverse. But I understand if you don't want to memorize all those, that's why we have the formula sheet. And the formula sheet, as always, is usually in your week 2 or your week 3 module. It's called Formulas from Calculus 1 and Calculus 2. Okay, and that's the one that we're going to go ahead and do here. So let me full screen that. Okay. Full screening this, zooming in. So I believe the one that we want is actually the integral of the square root of a squared minus u squared is sine inverse. That's this one right here. It's a little bit hard to see, but that's what it says. Zoom in even more. Oops. Okay, so it's sine inverse of u over a plus c. Okay, so going back to our problem, this needs to be written in the form square root of a squared minus u squared. So a squared minus u squared. So here we can see that a squared is 36. So that means a equals the square root of 36 which is 6. And then here u actually equals x. Okay? So here u equals x. So what we have here is the limit of the integral of du over the square root of a squared minus u squared, which, as I was just saying from your formula sheet, that ends up being sine inverse. Okay, so that's sine inverse of u over a plus c. But we're not going to write the plus c because we're going to end up doing a definite integral here. Okay, so we have the limit of sine inverse of u over a, okay, which is the same as the limit of sine inverse of, well, in this problem we said u was x and a was 6. Okay, so we actually have sine inverse of x over 6. And then remember, this is the limit as c approaches 6 from the left. That's what we said, right? Limit as c approaches 6 from the left. And again, we know it's the limit as c approaches 6 from the left because 6 was the upper limit of integration. If it had been the lower limit of integration, it would be the limit as c approaches that number from the right, which would be a little plus for the exponent. Okay, so what we got here is the limit as c approaches 6 from the left of sine inverse of x over 6. And then this is evaluated from x equals 0 to x equals c. Right, because we wrote in c instead of 6, because the original function was undefined there. Okay, so then plugging in here, we're going to end up with the limit as c approaches 6 from the left of sine inverse of the top number, so that's going to be sine inverse of c over 6. My 6's are starting to look like b's. They are looking a lot like b's. I don't know how many times I have to rewrite it. Still doesn't look like a 6. Okay, I guess that's better. And then we have minus sine inverse of 0 over 6. And if you're not too sure about sine inverse, you can use a unit circle is a good way to do it. Or if you have a calculator that will do sine inverse for you, that's even better. But that's even faster. Okay, so plugging in here, c, we're going to plug in 6 for c. And remember, when you're doing a limit, the funny thing about it is you just end up plugging in anyway. That's why I'm saying some people skip the whole limit part of these problems. Okay, so what we got here is sine inverse of 6 over 6 minus sine inverse of 0. Okay, and of course 6 over 6 is just 1. So we really just have sine inverse of 1 minus sine inverse of 0. Okay? So I'm going to show you the unit circle way. If you have a calculator that will do sine inverse for you, go for it. But the unit circle is really not that bad. Okay, let me actually get to the second page. Ooh, that looks bad. I think I'm going to actually go back and zoom out and try to download that as a PDF. Okay, let me open that up with my other PDF viewer. Okay, that looks a lot better. Okay, so for the unit circle, let me zoom in on that. It's on the second page of your formula sheet on the left side. Here we got our unit circle. So if we're going to do sine inverse, remember that sine of theta is the same as y on your unit circle. Okay, so recall sine of theta equals y. Okay, so we're just looking at our y-coordinate. So which y-coordinate gives us 1? So we look on our unit circle. So which y-coordinate is 1 is what I meant to say. So here, y is 1 when theta equals pi over 2. Okay? So that means sine inverse of 1 is pi over 2. Okay? So remember, sine of pi over 2 equals 1. Okay, because it's the y-coordinate and you're at 90 degrees as we just saw. So that means sine inverse of 1 equals pi over 2. Okay, and then we can do the same thing for sine inverse of 0. Okay, so sine inverse of 1 is pi over 2. We write that down. And then subtracting sine inverse of 0. Well, if you have sine inverse of 0, that's the same as saying sine of 0. I'm sorry, sine of theta equals 0. Okay, so what value of theta is going to give us 0 for y? Well, if we look at our unit circle, we can see that y is 0 when the angle theta is 0. So that's right here. Okay, so if sine of theta equals 0, that means theta actually has to be 0 as well. So sine of 0 equals 0, which means 0 equals sine inverse of 0. Or just use a calculator. Calculator's way faster. Okay, so we really have pi over 2 minus 0, which is pi over 2. Okay, so our answer is pi over 2. Alright, thanks for watching. And these can be a little frustrating because the limits end up not actually making a big difference. But I did want to show you the correct way to do type 2 improper integrals. Keep in mind that all of these problems, we could have just done them without the whole part where we write the limit. It's just that wouldn't be correct. Okay, mathematically, you are supposed to write them as limits the way we were. But technically, you could have just done it the old-fashioned way, where you just plug in the numbers and not even write any limits. It's just that that's not mathematically correct, but it still works. So if you want to take the easy way, just don't even write the limits. Just realize that that's not correct mathematically. Okay, thanks for watching.